Here's a quick question for you. How long does it take an attacker to move from initial compromise to full lateral movement in your network? In 2019, it was about 84 minutes. By 2022, it had dropped to just 21 minutes. And today, we're seeing breakout times as little as 7 minutes. 7 minutes. Now, here's the real question. How long does it take your cyber threat intelligence team to identify, analyze, and respond to a sophisticated threat? If you're like most organizations, you're measuring that in hours or even days. You're not losing because adversaries are smarter. You're losing because they are faster. And they're faster because they've figured out something that many CTI teams are still missing. I'm Adam from Craven Security, and today we're talking about the missing piece in modern cyber threat intelligence. The piece that separates teams from drowning in alerts, from teams that are actually ahead of the threat curve. We're talking about data science, data engineering, and machine learning in cyber threat intelligence. Let's jump in. Let's paint a picture of what most CTI teams look like today. We've got a team of smart analysts, people who understand TTPs, who can read through threat reports, who know the MITRE attack framework inside and out. They're good at what they do. But here's what their day actually looks like. Every single day, they're being hit with a tsunami of data. Endpoint logs, network flow data, authentication records, cloud telemetry. It's coming from everywhere, and it never stops. And what are they doing with all this data? They're manually pivoting through SIM queries. They're copying and pasting IP addresses from threat intel feeds. They're trying to correlate 3 different data sources using spreadsheets. They're reading through hundreds of pages of threat reports, trying to find that one paragraph that actually matters to their business. Any of this sound familiar? Here's the thing. This model worked when CTI was just about collecting static indicators of compromise, or sharing them in PDFs. When you could look at a list of known bad IP addresses and simply block them at your firewall. But that's not the game anymore. Modern adversaries are using automated ransomware frameworks. They're deploying polymorphic malware that changes its signature every time it runs. They're using domain generation algorithms that create thousands of new command and control domains on the fly. And increasingly, they're using AI, large language models that help them write better phishing emails, better code exploits, and adapt faster than ever before. You cannot fight automation with manual processes. You cannot fight machine speed attacks with human speed analysis. So, let's talk about what it actually takes to build a modern, data-driven CTI capability. And I want to be clear about something up front. This isn't about replacing analysts. This is about giving them superpowers. The foundation starts with something that sounds boring, but is absolutely critical: data engineering. Think about it this way. Before you can predict where an attacker is going, before you can train any machine learning model, and before you can do any kind of advanced analysis, you need to get your data house in order. And for most organizations, that house is currently on fire. The speed problem. Traditional security setups use what's called batch processing. Your logs get collected and processed maybe every hour or half an hour, or maybe even every 15 minutes. But remember those breakout times? 7 minutes? If you're processing logs in hourly batches, you've already lost. The attacker has moved laterally, established persistence, and is halfway to achieving their objective before your first alert even fires. This is why modern CTI teams are moving to streaming architectures. Tools like Apache Kafka act as the central nervous system for your security data. Instead of collecting logs and waiting, you're processing events as they happen, millisecond latency. And here's the beautiful part. That same event stream can feed your real-time alerting, your long-term data lake for historical analysis, and your machine learning models for pattern detection, all simultaneously. The relationship problem. But speed is only half the battle. The other half is understanding relationships. Here's an example. An IP address connects to your network. Your standard question might be, is this IP malicious? But that is the wrong question. The right questions are, what other IPs are connected to the same infrastructure? Which domains resolve to similar IP ranges? Are there shared SSL certificates? What malware families have historically used this infrastructure? Or what threat actors prefer this hosting provider? Perhaps there are timing patterns. How are these timing patterns related to the infrastructure that is deployed? The key is this. You're not looking at an isolated indicator anymore. You're looking at an entire ecosystem of relationships. And this is where traditional relational databases often fall apart. They're designed for structured queries. Give me all records where X equals Y. But threat intelligence isn't structured. It's a web of connections. And you need a database that thinks in graphs, not tables. Graph databases, like Neo4j, let you ask questions like, show me all domains that share infrastructure with known malicious IPs, and were registered in the last 72 hours by the same registrant used in previous APT campaigns. Try writing an SQL query for this. Good luck. In a graph database, it's simple, and it returns results in milliseconds. And this is how you move from collecting indicators to understanding infrastructure. From reactive blocking to proactive hunting. Alright, so now you've got your data pipeline humming, events are streaming in real time, you've got a graph database that understands relationships, and your infrastructure can actually handle the scale of modern security telemetry. Now comes the intelligence part, turning raw data into actionable intelligence. Problem 1. Finding needles in haystacks. Let's start with a classic CTI problem. How do you find the sophisticated, low and slow attacks that don't trigger any of your signature-based rules? This is where unsupervised learning can shine. Techniques like isolation forest and autoencoders don't need you to tell them what bad looks like. Instead, they learn what normal looks like and then flag anything that deviates from that baseline. Imagine you have a user who normally logs in from London between 9 and 5 PM every day. They access 5 specific servers during their daily work and download maybe 5 megabytes of data every day. Then, one Tuesday, that account logs in from Singapore at 3 AM, accesses 30 different servers, and downloads 10 gigabytes of data. Every individual action might be technically allowed by your security controls, but the patterns, that's not normal. And an unsupervised model would flag it immediately. But not because it matches a known attack signature, but because it violates the behavioral baseline established for this user. This is how you can catch the stuff that slips through traditional defenses. So here's another one for you. What do you do about domain generation algorithms? How do you detect them? Sophisticated malware uses these algorithms to generate thousands of seemingly random domain names every day. The malware tries to connect to these domains, and the attacker only needs to register 1 or 2 of them to maintain command and control. Classic indicator of compromise sharing does not work here. By the time you've added 1 malicious domain to your block list, the malware has already moved to the next 500. But machine learning models, particularly recurrent neural networks, can spot domain-generated algorithm domains by analysing the character patterns. You see, legitimate domains tend to have pronounceable structures and meaningful words, whereas DGA domains, they look like something has just smashed the keyboard to pieces. A trained model can identify DGA domains in real time with high accuracy, even if it's never seen that specific domain before. You're not blocking known bad anymore, you're blocking entire classes of malicious behaviour. And finally, we need to talk about the elephant in the room: generative AI and large language models. Here's where it gets interesting. Because LLMs are both a defensive and adversarial threat, on the defensive side, LLMs are already being used. They're being used to automatically summarize 100-page threat reports and turn it into actionable intelligence. And they're being used to convert natural language questions into complex database queries, or generate detection rules from plain English descriptions, and even correlate information across dozens of threat intelligence sources. That's hours of analyst work compressed into seconds. But here's the flip side. Adversaries have access to the same technology. We're seeing threat actors use LLMs to craft more convincing phishing emails, write better exploit code, and even conduct social engineering at scale. The implication? If you're not using AI to defend, you're at a structural disadvantage against adversaries who are using it to attack. Okay, so right now you might be thinking, Adam, this all sounds great, but I'm not a data scientist, and I don't know how to code in Python or build streaming pipelines. My team barely has time to keep up with daily alerts, let alone implement machine learning models. I get it, and I want to be really clear about something here. You don't need to become a data scientist to benefit from data science. What you need is data science thinking. You need to understand what's possible, where the bottlenecks are, and how to ask the right questions. Firstly, start with your pain points. Don't try to boil the ocean. Start with the specific problems that are burning the most analyst hours in your team. Spending hours manually correlating IOCs across platforms, or constantly fighting false positives in your alerts, or maybe missing sophisticated attacks because they don't match any of your known signatures. Or maybe you're unable to keep up with the volume of threat intelligence reports. Just pick one. Just one. And then ask, could this be automated or augmented with the right data infrastructure or machine learning model? Prove value on that one single use case. Show your leadership team that implementing streaming ingestion reduced detection time from 2 hours to just 3 minutes. Show them that the anomaly detection model caught 3 intrusions that signature-based rules might have missed. Then, once you have that concrete piece of evidence, scale from there. At step 2, you want to build and buy strategically. You don't have to build everything from scratch. There are commercial platforms now that provide streaming ingestion, graph databases, and pre-trained machine learning models out of the box. Microsoft Sentinel, Splunk, Elastic, they all have built-in machine learning capabilities. You can start using their anomaly detection without even writing a single line of code. But, and this is important, you need to understand the fundamentals so that you can evaluate these tools effectively, configure them properly, and interpret their results intelligently. A vendor's AI-powered threat detection means nothing if you don't understand what kind of model they're using, what data it was trained on, and its false positive rate. Step 3 is all about investing in hybrid skills for your team. The most valuable people in CTI moving forward are going to be the ones who can bridge 2 worlds. First, they have a deep understanding of adversary tradecraft and intelligence operations. And second, they have practical data analysis skills, querying databases, writing basic Python scripts, and understanding statistical concepts. Now, you don't need a PhD in machine learning, but learning the basics of SQL, Python, and some data analysis skills, now that is achievable. And that will 10x your effectiveness as a threat intelligence analyst. There are resources out there specifically designed for security practitioners looking to up their data analysis skills. You have Jupyter notebooks for threat hunting, Python libraries for working with threat intelligence formats, and open source frameworks for building detections. The tools exist. The knowledge is accessible. What's required is the commitment to evolve alongside the threat landscape. If you want to dive deeper into any of these topics, whether it's building streaming pipelines, working with graph databases, or implementing specific machine learning models for threat detection, drop a comment below. I'm particularly curious, what's the biggest data challenge you're facing in your CTI team right now? And if you're serious about developing these skills in your own career, check out the coaching and courses available at Craven Security, link in the description. Until next time, stay curious, stay technical, and remember, the best defense is the one that thinks like a data scientist.